Theorem 5 says if you have a function y equals or f of x equals e to the x, its derivative is simply e to the x. That's what they are saying. It's a super cool function because derivative is the function itself. So why is that true? So I want to show you that. I want to prove that with you. Prove this theorem 5 with you in this video because the application is super easy. Take a look at example 1. If I have y equals 3e to the x, the derivative y prime or dy dx is simply 3 times e to the x. I guess I can make this longer by saying something like, oh, dy dx equals 3 times the derivative of e to the x. And that is just 3 times this part right there. It gives us e to the x. So that's what it is, but if it is just a constant, like I can make a little rule here. Rule derivative of any constant k times e to the x, any constant k times e to the x is just really k times e to the x. Okay? Just having a number in front of the k, in front of the e to the x term, the derivative is just going to be itself. So if you look at b right here, if the function is y equals negative 5e to the x, its derivative is itself. So if I make up another problem, just one more, see if you have y equals half times e to the x, as long as you just have a simple number in front of the e to the x and the exponent is simply x, then the derivative is just going to be itself. Super easy, right? We're gonna have to apply chain rule a little bit later, but for right now, example 1, that's what it is. That's what it is. And why is that true? That's what I want to show you in this video. This is the first video of section 2.2. In order to prove that, we need to get this piece graphically first. Let's find what this blue piece is graphically, okay? Hold on, let me write this down. What is limit of e to the h power minus 1 over h as h approaches 0? And I will do this graphically, which means I'm going to go to my Desmos graphing calculator real quick. Let me open that browser up. Desmos graphing calculator. And I will graph this. E to the h minus 1 all of. Maybe I need to just use x for right now because I think Desmos doesn't like it when I use h. All right, hold on. So I'll open up a fraction first. Okay. And I'll say what was on top with the fraction. I'll just do e to the x minus 1 over x, okay? So as x approaches 0, where is the function value going? Okay, so take a look. As x approaches 0, from the left, it's going to 1. From the right, it's going to 1, right? So we can't really have a point at 0 because when h is 0 or x is 0, the function is undefined because x or h is in the bottom of the fraction. But as we can see from this graph, from the left it's approaching a y value of 1. From the right it's approaching a y value of 1. So the limit is 1. Okay, so we got that from graph. And you're wondering, why do we need this? This is an important piece of puzzle we need in order to prove this theorem number 5. So I'll prove that theorem here with you. It says use the definition of derivative to find f prime of x. So what is definition of derivative? You know, the one with the difference quotient. So f prime of x is, we have to say that in the limit h approaches 0 of that difference quotient, f of x plus h minus f of x all over h. Now we're using the function f of x equals e to the x. So that will be, you have to keep on writing that limit as x approaches 0 until we actually plug in h equals 0, okay? So f of x plus h. So I need to plug in x plus h into this function. So what will that be? That will be e raised to the x plus h power, right? And I need to do minus f of x minus e to the x all over h. I'm going to rewrite that first term, okay? Do you agree that e to the x plus h power is the same as e to the x times e to the h, right? So I am unsimplifying this. If you separate these, you can write it as e to the x times e to the h minus e to the x over h. What do they have in common on the numerator? Notice that they both have e to the x in common, so I'm going to pull that out to the front, okay? In fact, I will pull it out all the way outside, e to the x. And I get to pull it out all the way outside because this term e to the x doesn't have h in it, so it doesn't matter that I'm plugging in h equals 0. I can just pull it out in front of the entire limit notation, right? So limit as h approaches 0, what is left inside here? The orange parts went outside, right? The orange piece went outside. So what's left? I have e to the h minus 1, right? Because you have to do e to the x divided by e to the x. So some people think, oh, it cancels out, but it actually becomes 1 and all over 1. And guess what? Take a look at this part. This right here is what we saw graphically to be 1, right? So the whole thing becomes e to the x times 1 or e to the x. So we just proved that the derivative of e to the x comes out to be e to the x. So now we proved it once. We can use that theorem 5 all we want to solve some derivative problems. But I don't know, I think this is pretty nice, right? I may put this on your test too. I want you to prove it to me that the derivative of e to the x is e to the x using the limit definition of derivative. It wasn't that cute. I like that. All right, so in this video, I showed you what derivative of e to the x is. Did a couple very easy examples, and the top part right here, this was actually proving this theorem using the definition of derivative. I will come back and talk to you about theorem 6 in another video very soon.